Hey guys, so in the last video we talked about complex numbers, and now I want to show you something really cool and extremely useful about complex numbers, and it is called the complex exponential. And this says that this is e to the ix, right? E is Euler's number, about 2.71828, and I is the imaginary number, the square root of -1, and x is anything, right? And there's something called Euler's formula, and Euler's formula gives this a little bit of sense to it, right? Because, you know, we kind of understand what it means to raise something to a power, right? It's in a way repeated multiplication, right? But what about an imaginary power? What happens if you raise something to an imaginary power? That's answered by Euler's formula. E to the ix. E to the ix is equal to cosine of x plus I sine of x. Now this is a very weird formula, right? We've got this exponential, and now we've got trigonometric functions, right? And this is in standard notation. You can see that the real part of e to the ix is cosine of x, and the imaginary part is sine of x. Right? So it's a weird formula. Now there is a beautiful proof of it. I'm not going to do it in this video. If you have taken like a Calculus 2 class, you should be familiar with Taylor and Maclaurin series. And what I'll tell you is take e to the ix, right? And make the Maclaurin series for e to the ix, right? Which is 1 plus x plus x squared over 2 plus x cubed over 3 factorial plus x cubed over, or x to the fourth over 4 factorial, etc., etc. Instead of x, make it ix. Then, right, we know the powers of I, so you can write it out, and you'll have them alternating signs in a way with imaginary numbers. Then you separate out the real and imaginary part, and then compare that to the Taylor series for cosine of x and the Taylor series for sine of x. And what you'll notice is Euler's formula. So if you know what I'm talking about, that's great. If you don't, if you're not familiar with Maclaurin series, that is perfectly okay. You just need to know that this formula works. And I will show one thing that can kind of half-prove this formula. But first of all, I just want to make one generalization, right? This is e to the ix, but often, right, x can be anything. But if we're talking about it as a variable, it's sometimes useful to talk about e to the iax, which is, right, you're just, instead of x, you're plugging in ax, so that's cosine of ax plus I sine of ax. All right, and now this is not a proof of the formula, but just something to show you kind of that it does work, at least, you know, in certain situations, and it will work in all situations. But I'm going to take the derivative of this, right? So if I want to take the derivative of this, right, and I'd be taking the derivative of this too, right? Because if they're equal, the derivative of this side should be equal to the derivative of this side. So let's see if we can show that that is true. So when I do this, right, using our e to the x rule and the chain rule, it's pretty easy to show that this is IA times e to the IAX, right? And if I take the derivative of this side, right, derivative of cosine of ax, that's a times cosine, or sorry, a times the negative sine of ax. So I'll put the negative out front. Negative a sine of ax, right? And the derivative of sine right? This is equal to, then we're adding this with, right, I, constant coefficients rule, IA, from the chain rule, times the cosine derivative of sine is cosine of AX. Right? And now, let's just look at this side. So I'll do this in a different color. If I look at this side, IA e to the IAX, right? Well, this is IA times cosine of x plus this is IA times cosine of AX plus I sine of AX. And if I can just do this sort of the distributing in my head, this is going to give me IA cosine of AX, right? Plus IA times I sine of AX. The I times I will be a -1, so this will be negative A sine of AX. And indeed, these are equal to each other, right? That's in the opposite order. So I strongly encourage you to also show that this works with integrals. Take the integral of both, the indefinite integral, or also known as the antiderivative, right? And we can do the reverse chain rule for that for a constant coefficient, right? In the embedded function, we know how to do that. Do it, and you'll find the exact same thing that it holds. All right. So I'm actually gonna do this. Got rid of what we just did. Okay. I wanted to keep that first expression without the derivative part, but I'll rewrite it. So just to rewrite what I just erased, I've got e to the IAX equals cosine of AX plus I sine of AX. Now there's just a few less things that I want to do. First of all, let's look at what e to the minus IAX is. Right? This could be right, well, this is e to the minus IAX. It's not just, we could let a be negative, but I want to look at what this is, see if we can kind of find any parallels between this. So e to the minus IAX, well, that's going to be cosine of negative AX, right? But cosine is an even function, right? So we know just cosine of, right, negative AX, since it's an even function, that's cosine of AX. And I wrote that line, it's just a quick note, right? And sine, if we remember, is an odd function. So this is going to be cosine of negative AX, but that's just the same as cosine of AX, plus I times the sine of negative AX. But the sine of negative AX is negative sine of AX, right? So let's just make this minus I sine of AX. Right? And what does that show us? Well, this is cosine of AX plus I sine of AX. This is cosine of AX minus I. These look like complex conjugates of each other, and indeed they are. So I'll just write that here. I'm going to write in yellow here. E to the IAX star is equal to e to the minus IAX. Make sure you write that down. That is very important. Complex conjugate of a complex exponential is the complex exponential with a negative exponent. All right. Now, finally, the last thing I want to look at, hopefully you have all of this written down, is the absolute value of e to the IAX. Right? Let's look. The absolute value of e to the IAX. What I'm actually going to do, I know I erased it again. I'll just write this here. This is IAX, cosine of AX, I sine of ax. Right? We can do that here. All right. So I want the absolute value of e to the I ax. Well, that's just the square root of cosine of ax squared, right? So cosine squared of ax plus the imaginary part is sine of ax, so plus sine squared of ax. But cosine squared of something plus sine squared of that thing, that is equal to 1. That's the Pythagorean identity. So the absolute value of a complex exponential, the norm or magnitude of a complex exponential, is 1. That is also very important. And we can also see that knowing that right, the norm of e to the I ax squared is equal to e to the I ax times e to the I ax complex conjugate. But e to the I ax complex conjugate is e to the minus I ax, right? So this is e to the I ax times e to the minus I ax. But e to the minus I ax is just 1 over e to the I ax. So this is, it's multiplying something by its reciprocal. This is 1. And indeed, we get the same answer. All right, so that is complex exponentials. They are incredibly important. So make sure you understand what's going on here. All right.